My dear friends, welcome back to Be Spice. This is Bala with you. In this session, we are going to talk about mastering analyzer, wherein we'll focus on pH analyzer. So the analyzer one is a long pending one, friends. So that is why I, thought of, bringing you this item, mastering analyzer. So we will start with pH, then we'll go to conductivity, then ORP, like sense. So all kind of analyzer we will cover in this session. Okay. So let's move on with the agenda. The agenda, a lot of questions actually. Uh, why pH is monitored? Typical pH analysis point. Where and all we use this? Typical. Then the basics of pH and the pH and some common solutions. Yeah. Then measuring pH, the principle. Okay. Measuring electrode and also the reference electrode. Then we have a combined electrodes. And of course, without Nernst equation, we can't, close this pH. So Nernst equation also we are going to cover. See, friends, this may be a little bit, lengthy, but it's all concepts. See, of course, concept is important, right? Concept, we need to know the concept, right? Yes. So that is the intent of this session. Okay. Now, why pH is monitored? The water flowing through the piping and components in the plants should be maintained. Agreed? Okay. If it get acidic, then it can cause corrosion. Agreed? Okay. If it is highly alkaline, then it may cause scaling. Agreed? Yes. So hence it is essential to have pH checks at some location of the flow circuit. You got it, friends? So we have answered why pH is monitored. Okay. Typical pH analysis point. Boiler water, economizer, inlet or feed water. A typical. There are many more, but I just put typical. Okay, friends? Okay. Basics of pH. pH is what? Activity of hydrogen ion, which defines the character of a solution. Right, friends? Okay. What is the formula? pH is equal to minus a logarithmic of 10 H plus. That is the hydrogen ions. Okay. So pH gives an indication of the degree of acidity or alkalinity of aqueous solutions. Right. Scale of pH is 0 to 40. Okay. So ratio of H plus ions and OH minus ion is equal, then pH is 7, right? pH is equal to POH is equal to 7, right? So more positive ions, more acid. Less positive ions, more alkaline. pH is a dilute solution measurement. I hope the basics is clear, right? Okay. Now, pH and some common solution which we encounter during our daily life. You can see here, friends. First, we go to bear. You see, bear is here actually, between this 4 and 5, right? Then tomato juice 4. Coca-Cola, yes, you see the pH 3. Then cheese between 5 to 6. Then you see 6 to 7 milk. Okay. So then all this after 7, this is neutral, pure water neutral. Then gin you can see 8 to 9. Then you have a liquid soap 10 to 11. Then washing soda here in this area. Okay. So these are the things, friends. Okay. Just to give you some idea. Okay. Right. So measuring pH. pH measurement makes use of a hydrogen sensitive glass electrode. Okay. pH measurement makes use of a hydrogen sensitive glass electrode. You can see here, this is a pH measuring electrode. This is the reference electrode. And here we are measuring the input impedance. Okay. Right. So this forms one half cell of an electrochemical cell. Okay. Hydrogen sensitive glass electrode. This forms a one half cell of an electromechanical cell. The other half comprises the reference electrode that is immersed in the same solution. Okay. A high impedance input voltmeter used to measure the EMF of the two electrodes. So this is the basic funda. Okay. Now we'll go into the detail. Measuring electrode. Okay. Measuring electrode comprises a glass envelope containing a buffer solution of known ionic strength and pH. This is the typical measuring electrode. You can see here the membrane, the internal buffer, the lead element, the glass envelope. Okay. So it basically comprises a glass envelope containing a buffer solution of known ionic strength and pH. A silver wire coated with silver chloride is immersed in the buffer solution and forms the measurement lead wire. This one, lead of element here, right? Yeah. A sensing element at the tip of the electrode is a hydrogen sensitive membrane, okay, manufactured from special glass containing alkali and alkali earth and rare ions. So this is the funda. Okay. So pH measurement is based on chemical reaction that takes place between the sample solution and the membrane surface here, generating an electrical potential that varies the pH value. Very simple, right? I hope this is clear. Okay. Now we look, bit of, the chemistry, what do you call the reaction, or maybe the structure, mechanism. Mechanism involved is dependent on the hydration of the glass membrane surface, which forms the gel layer. That is the hydrated silica when the electrode is in contact with the aqueous medium. Okay. Due to the presence of encapsulated internal buffer, a gel layer is also formed on the internal surface of the glass membrane. The positive charges on the water molecule attract the Cl minus ions and the negative charges attract the Na plus ions. As you can see here, this is the yeah, this is the okay, maybe I'll go here. You see the positive charges, it attract the Cl minus. You see it, the arrow pointing towards, right? It's Cl minus. Okay, friends, right? Then you have the negative charges that attracts the Na plus ions. That's it, right? Okay. So this is the mechanism involved. Okay. As a result of this, the water molecule form a cage-like formation around this Na plus and Cl minus. Okay. So negative poles of the water molecules dipole pointing towards them Na plus cation. Then positive poles of the water molecule pointing towards the Cl minus. You're clear, friends? Okay, got it right? Right. Okay. So you see this is the negative and this is the positive, right? Okay. So here's some mechanism, friends. I try to explain as much as possible. Yeah, it's all happening, what is inside the surface, the surface of this. Maybe I'll go back here, want to explain here, here, right? This membrane, yes. This is what I'm going to explain in this, what is happening here, right? You can see here, yes. So a singly charged alkali metal cation, you can see here, L plus, you see, L plus, all right, in the glass are exchanged for the hydrogen ions. You can see here, L plus, H plus, all these, right? Yes. In the solution, giving rise to a potential boundary at the surface, potential boundary at the surface of the hydrated glass layer. Diffusion of hydrogen ion, this is the one, diffusion of hydrogen ion, that is acidic solution, that is in basically, diffusion of hydrogen ion in, you can see hydrogen ion in acidic solution or out, okay, alkaline solution of the gel layer occurs, diffusion, okay. So this diffusion leads to a buildup of the charge at the outer phase layer, okay, and a new equilibrium state exists which prevents further hydrogen ion transport, okay, right. So the metal ions in the glass membrane are responsible for the migration of the charge. You see the metal ions in the gas membrane, right? Glass membrane are responsible for migration of the charge to the gel layer on the inner surface of the membrane. You see, this is the gel layer. You can see, this is the gel layer. So basically the metal ions in the glass membrane, okay, are responsible for migration of the charge to the gel layer on the inner surface. You can see here the inner surface of the membrane. So this is the potential difference that allows the pH measurement to take place. So that is the principle, friends. I hope it is clear, right? Anything you can write to me, friends. Anything if you want to clarify. Of course, for instrumentation point of view, I think this is more or less is okay from my point of view. Yeah. Yeah. Now we talk about the reference electrode. This is the typical reference electrode. Okay, the measuring electrode forms only one half cell of the pH, electrochemical cell. So in order to complete the measurement circuit, it must be combined with other half cell, that is the reference electrode. In practice, reference electrode causes more problem than measuring electrode. Any deviation in its potential will cause overall potential to change, thereby causing a overall pH reading to change, right? So the reference electrode comprises an internal reference element. You can see here, internal reference element immersed in the electrolyte solution, both housed in the glass or plastic envelope. A salt bridge forms the liquid junction between the electrolyte and process liquid being measured, thus completing the pH measurement circuit. A salt bridge forms a liquid junction between the electrolyte and the process liquid being measured. Okay, I will explain the salt bridge even in the subsequent slides. Now get to the concept. The salt bridge forms a liquid junction between the electrolyte, okay, and the process liquid being measured, thus completing a pH measurement circuit. Okay, now you see here, friends. Yeah. In some electrode, silver chloride wire is immersed direct into the internal electrode. You can see here, this is the silver chloride, right? Yes, silver chloride, right? Silver chloride element. This is directly into the internal electrolyte. This is the directly, right? In some cases, the construction. In others, the wire is surrounded by silver chloride crystals within the glass cylinder. Silver chloride, you see here, silver chloride crystals within the glass cylinder and separated from the electrolyte, okay, by a cotton wool plug. You can see here, this one, cotton wool plug. The wire is surrounded by silver wire crystal, okay, crystals within the glass cylinder and separated from the electrolyte. This is the electrolyte, right? Using this glass, okay, cotton wool plug. Okay, the internal electrolyte solution should fulfill the number of conditions. What are all those conditions? Should have a high ionic strength. Okay, then should be stable, should not react to the process solution. Of course, yes, should be soluble in process solution. So the diffusion rates of cation and anion of the electrolyte salt should be approximately equal to prevent the buildup of the charge across the liquid junction, okay, which can cause offset errors. Friends, this one I want to give you an idea what is reference light and how the look and feel. That is the intent actually. Okay, yeah. The migration of velocity for ions is determined by their charge and size. Okay, so to add on few more, the reference junction, I told you now the salt bridge, right? So this is the salt bridge. The reference junction or the salt bridge, liquid junction or filter forms the interface between the process solution and the internal electrolyte. Okay, so this one. Okay, so this is the salt bridge actually. It forms the interface between the process solution and the electrolyte. Okay, and completes the electrical path for measuring electrode to the reference electrode. So apart from allowing small amount of electrolyte to flow through it, the reference junction should also be chemically inert so as to not interfere with the ion exchange process and should also maintain a low consistent electrical resistance value. This is also a concept. Okay. So we have seen reference electrode now. Now we are going to see combined electrodes. In practice, friends, normally, see, whatever we have covered is more of a theory. Okay. In practice, nowadays, measuring and reference electrode are usually combined into a single unit. You can see here, this is the reference element and this is the measuring electrode. Okay. So this is the salt bridge. So you may ask why you explained all this. Yes, I explained this because to give you an idea what is a reference and what is, measuring electrode, all these, what is inside. It should give you as an idea. But in practice, the measuring and reference are usually combined into one single unit. Okay. The reference electrode is arranged concentrically around the measuring electrode. This is your measuring electrode, right? So the reference element is arranged concentrically around the measuring electrode. Okay, friends, you got it? So the combination electrode is much easier to handle and is used almost exclusively in industrial application. So that is the point. Separate electrodes are recommended when two electrodes are expected to have very different life expectancies. That is also we need to take note of. Okay. So now we go to the Nernst equation. I told you, right? Without Nernst equation, we cannot complete this pH. So here E, what is this E? Potential generated, that is in millivolts, is equal to E0, e to the power 0, 0. Okay. That is a standard cell potential. Okay. Then R is a universal gas constant. Okay, right? Then T, absolute temperature. Okay, that is the absolute temperature T. Then N is the valency. That is the charge of the ion. N is equal to 1 for H plus ion. Then F is the Faraday's constant. H plus is the hydrogen ion concentration. So E is equal to E to the power 0 plus 2.303 into RT by NF, a logarithmic of H plus. This is the Nernst equation. In a Nernst equation, friends, if you remember this, I think we would have studied during our college days. 2.303 RT by NF. This is called the Nernst or a slope factor and is given as a symbol N. So then the equation becomes E is equal to E to the power 0 plus N multiplied by the logarithmic of hydrogen plus hydrogen activity, hydrogen ion concentration. Right, friends? So Nernst equation is clear, right? Okay. So at 25 degrees, this is very important, practical. At 25 degrees centigrade, if pH changes from 7 to 8, the voltage output will change from 0 to 59.16 millivolt. Similarly, a change in pH from 8 to 9 will result in a voltage change from 59.16 to 118.32 millivolt. Okay. So this is the table. This is the pH. This is the delta pH, and this is the Nernst equation. You can see here 0. This means pH 7. Then 1 means plus 6, 2 plus 5, 3 plus 4, 4 plus 3, 5 plus 2, 6 plus 1, 7 neutral, that is 0. Then 8 minus 1, 9 minus 2, 10 minus 3, 11 minus 4, 12 minus 5, 13 minus 6, then 14 minus 7. This is how it works. So accordingly, we have this voltage. If you see here, the pH changes from 7 to 8. Okay, this one, 7 to 8. There you can see it changes from 0 to 59.16. Either way, 7 to 8. Here it is negative, here it is positive. Okay, friends. Similarly, a change in pH from 8 to 9. You see, from 59 to 118. 59 to 118. So this is how it works actually. Right, friends? So with this voltage, we can see this pH. Got it? Right. So this is a typical graph. Okay. Now, little more. Temperature effect. You see the temperature effect here. 5, 10, 15, 20, all these, right? So how it affects actually. You see here, 5 temperature. See 55.19 millivolt, right? So accordingly, we have various 10 means 56, 15 means 57, 20 means like this. Okay. So we can correlate here. This is on the temperature effect. Okay. That's it, friends. So yeah, I hope you got some insights on this. Okay. So we will see now. I think we know the concept like little bit on the pH. Next video, we will see the data sheet actually, which is very important for us. Okay. So thank you. Bye bye. Take care.